know how much detail you went into when you talked about electron configurations, but magnetism is a direct result of electrons, of unpaired electrons with their spin facing the same direction. So pretty much everything we talk about in chemistry is electromagnetic force. And the electromagnetic, when we look at electromagnetic force, energy looks a little different. Before I go into that in more detail, since that's where we're going to spend the bulk of our time, just to finish up the last two forces, fundamental forces that you see in physics or in the universe commonly are strong and weak nuclear force. And basically we have to zoom in even further to look at, instead of looking at something at the atomic scale, we're looking at something where forces are acting at the nuclear scale. So about 2,000 times smaller than the size of a 1s orbital. Again, not sure how much you talked about the different scales of atoms, but if you picture going to a baseball park, to Oracle Park, or going to the Coliseum in Oakland, if you picture standing on the pitcher's mound and holding a baseball, that baseball is the size of a nucleus, and the rest of the stadium is about the size of your electron cloud. So we're really zooming in when we start talking about strong and weak nuclear force, which we will once we start talking about nuclear chemistry. That's a whole nother level zoomed in beyond what we're talking about right now. So for now, we're going to talk about energy in the context of electromagnetic force and in chemicals and molecule level. And so that energy all comes from our kinetic energy at the molecular level is basically observed as temperature. How hot something is a measure of how fast the molecules are moving. Right? Because all temperature really is sort of measuring that what's the word I'm looking for? It's measuring the average kinetic energy of the entire system of molecules and kind of converting that into something that we can measure in terms of temperature scales. Potential energy at a molecular level is the energy that you find in chemical bonds. Basically, chemical bonds are electrons at different energy levels, right? When you get electrons at the right energy levels and they are able to overlap the orbital shapes, we get chemical bonds forming. Those chemical bonds have an energy associated with them. If you take an unstable chemical bond and you break it and allow the electrons to rearrange themselves to become more stable, oftentimes that releases energy. So that's why we think of chemical bonds as being sort of energy storage for a molecule. Chemical bonds in a large molecule that energy can get released, and in doing so, that changes the temperature of the surroundings, which is another way of saying that it's changing the amount of kinetic energy around it or doing work to the surroundings. So for instance, the classic example is burning gasoline. Burning gasoline is releasing a lot of high energy electrons to rearrange to form lower energy bonds. Carbon-carbon bonds and carbon-hydrogen bonds, like you see in gasoline, are not particularly stable. If you allow them to react with oxygen, you make CO2 and water, both of which have bonds that are much more stable. And in doing so, you release energy to the surroundings. And so that type of reaction, anytime you have a reaction that releases energy to the surroundings, in other words, makes the surroundings warmer, we call that exothermic. Exo from external, from the same root as external, thermic meaning heat. So in other words, we're giving heat to the surroundings, giving heat to the exterior. There are reactions that go the other way. So for instance, if you have a reaction, there's some ionic compounds that when you dissolve them in water, you actually have to put energy in to break them apart. So you're actually making things less stable in a way. And those type of reactions where the surroundings get colder are called endothermic reactions. endothermic. And the root endo means internal. So basically you have to put energy, you have to put heat into your chemicals in order for an endothermic reaction to happen. So endothermic reactions make the surroundings colder. Exothermic reactions make the surroundings warmer. So that's all well and good as long as we're only talking about like we're just talking conceptually. If we want to actually be able to measure something though, we have to look at it in terms of, we have to have some way to measure this energy. And I just got done telling you about how kinetic energy at the molecular level is measured as temperature. So anytime we're talking about a change in energy, we're going to relate it back to a temperature change. All right, but before we do that, we have to define some units for energy. Our most common units we use in chemistry are calories and joules. So calorie is the amount of energy that it takes to raise the temperature of 1 gram of water by 1 degree Celsius. So basically it's just a way of saying, okay, if I'm measuring the temperature change of a bottle of water, I can tell how much energy went into it by how much the water in physics defined as 1/2 mass of an object times its velocity squared. Which we're not going to do a whole lot with that, but if physicists are choosing the unit